Hi everyone. In previous videos, we've been learning about nuclear fission, and we've seen some examples, we've done some calculations involving nuclear fission, and now we can start talking about the practical applications of fission, both the destructive applications like atomic bombs and the constructive applications like nuclear power plants. In order to be able to understand how both of those applications work, we need to understand this idea of a chain reaction and see how it might apply to nuclear fission. To help us understand this, we're going to make use of an example that we've seen already in previous videos. And that's the example of a uranium-235 nucleus absorbing a neutron. We've spoken in a past video about how when this uranium-235 nucleus absorbs a neutron, it will split into smaller daughter nuclides. Specifically, one of the things that it might split into is barium-141 and krypton-92. And then we spoke about how to balance out the mass number in this equation. I would need 3 neutrons to be released as well. Now, before I move on, I just want to make it really clear what's happening here. This looks like a classic chemical equation where I would have uranium reacting with a neutron to create these products. So I just want to make it really clear that that's not what's happening. The uranium is not reacting with the neutron. Instead, it's more like a two-step process, actually, where the uranium nucleus is absorbing the neutron to become uranium-236. And then, since uranium-236 is so unstable, the uranium-236 will, in order to become more stable, in order to increase its binding energy per nucleon, which we've spoken about before, it will split into the barium and the krypton and the 3 neutrons. So it's more like a two-step process, what's happening. But we write it as one. I just want to make it really clear that that's what's happening. It's not the uranium reacting with the neutron. It's the uranium nucleus absorbing the neutron, becoming unstable, and therefore splitting into the daughter nuclides and the 3 neutrons. What you'll notice here is that these 3 neutrons, if we think about it, one of those, or even 2 or 3 of those neutrons, could potentially be absorbed by another uranium nucleus, and therefore set off this whole process again. Let's draw a diagram of what that might look like. If I start with 1 uranium nucleus, and I can get it to absorb a neutron, that initial uranium nucleus will undergo nuclear fission, and it will release, if it undergoes nuclear fission according to this particular equation, it will release 3 more neutrons. Now, if I can create the conditions such that some or even all of these 3 neutrons released will be absorbed by another uranium nucleus, then each of those further 3 uranium nuclei will undergo nuclear fission themselves and release 3 more neutrons. And of course, this could continue. Now, remember that each time this happens, each time a uranium nucleus releases 3 neutrons, there's some other stuff happening as well. It's also splitting into barium and krypton, and it's also, because of the nuclear fission, releasing an enormous amount of energy. Now, each of these 3 neutrons that each of these uranium nuclei is releasing could, of course, be absorbed by another uranium nucleus, and then each of these would release another 3 neutrons and undergo nuclear fission themselves. And hopefully, what you can see is that as this continues, the number of uranium nuclei undergoing nuclear fission will increase exponentially at an ever-increasing rate. Now, this idea, where I start off the first reaction, all I do is I get this uranium nucleus to absorb 1 neutron, And then if I can create the conditions correctly, the rest will happen by itself. More and more uranium nuclei will undergo nuclear fission. This is what I call a chain reaction, where I set off the first thing and the rest happens on its own. Now, I'm going to leave it to future videos to explain exactly how this is utilized in specific technologies, but for now we can start thinking already about how this would work. If I let this continue to grow without any intervention, without it slowing down or stopping at all, until all the uranium nuclei that I had undergone nuclear fission in a very short amount of time, then that would, as you can imagine, release an enormous amount of energy all at once in the form of an explosion. And that's how a nuclear bomb works. It causes this chain reaction where it's not slowed down or stopped at all, and there's just an ever increasing rate, an exponentially increasing number of uranium nuclei undergoing nuclear fission until the whole thing releases all the uranium nuclei I have, release their energy as they undergo nuclear fission in a very short amount of time, creating a very large explosion. On the other hand, if I can somewhat control this reaction, let's say I can make it so that each uranium nucleus, when it releases the 3 neutrons, if I can make it that only one of those neutrons actually is absorbed by a further uranium nucleus, then it means that the chain reaction will look more like this. And it will be a little bit more controlled. And you can start to see how this sort of process, where I control the rate of this chain reaction, might be able to be used more constructively, like in a nuclear power plant, where I have this reaction occurring without my active input, and yet it's not going out of control and creating an explosion, but is happening at a steady rate, not an exponentially increasing rate. So the main point of this video was to understand what this chain reaction is and how it occurs. A chain reaction is when one uranium nucleus undergoes nuclear fission, and then the neutrons that it releases are absorbed by further uranium nuclei, which undergo nuclear fission themselves. When I can get this to occur, the reaction becomes a chain reaction where I have this first active input to get it started, but then no further active input is needed to keep the reaction going. If that reaction then goes out of control, increasing exponentially, then it will become an explosion. And if I can control that rate of reaction, then I can harness that power more productively in a nuclear power plant. I'll leave it to a later video to explain how each of those things work respectively.